Alright, thanks for watching, and today we would like to talk about metric spaces, which are a very useful and powerful generalization of the real numbers and of absolute values. Because if you remember absolute values, there was one identity that we used over and over and over again in this course, which is what? Exactly, it's the triangle inequality, which simply says that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And from that we deduce a nice corollary which simply says that the distance between a and c is less than or equal to the distance between a and b and the distance between b and c. And we interpreted this as saying that the length of the leg of one triangle is less than or equal to the sum of the other two legs. Of course we use this a lot, but there were other properties which we unconsciously used without even thinking about it. Namely, first of all, the distance between x and y, it's always non-negative, so hopefully that is clear. Moreover, the only way the distance between x and y is 0 is if the 2 points are the same to start with. Also, the distance between x and y is the same thing as the distance between y and x. And lastly, of course, the triangle inequality, which is just saying that the distance between x and z is less than or equal to the distance between x and y and the distance between y and z. Now, what's the idea behind a metric space? Suppose we forget everything about the real numbers, like in the matrix, except for those 4 properties. It turns out the stuff that we get, which is called a metric space, isn't so different from the real numbers after all, which really shows that those 4 properties are really the essence of the real numbers. So now, without further ado, let me define a metric space. So, definition, let S be any set. Then we say SD, so not San Diego, but the set S with a distance function d is a metric space if the following 4 conditions hold, and don't be shocked, those are pretty much the same as the beginning. Namely, the distance between 2 points is always non-negative. The only way the distance between x and y is 0 is if the 2 points are the same to start with. And the distance between x and y, it's the same thing as the distance between y and x. And last but not least, the distance between x and z, it's less than or equal to the distance between x and y plus the distance between y and z. Alright, and seems like a weird definition, but similar to before. And really to show you how powerful this is, let me give you 10 examples of metric spaces that occur in nature. Okay, so some very important examples that you'll see throughout this course, and except maybe the last 2. They're a bit exotic, but so. Again, metric space, any set with a distance function that satisfies the following properties. Well, of course, the first example is the one we've seen before. So the real numbers with the distance simply being distance between x and y is the absolute value of y minus x. And then, well, there are other metrics on metric spaces like that, but to get more interesting examples and more natural examples, let's go 1 dimension higher. So consider, and don't laugh, but R2 with the metric D2 So literally R2, D2, where the distance between 2 points, and I apologize for this notation, but it's the one that the book is using. So the distance between x1 and x2 and y1, y2 is just the following. It's just the usual distance. So this is D2. So D2 between x1, x2 and y1, y2. And again, sometimes I'll mix them up, so just my apologies. It's just the square root of the sum of squares. So y1 minus x1 squared plus y2 minus x2 squared. Okay, just the usual distance. So for instance, d2 of 1, 2, and then 3, 4 is just the square root of 3 minus 1 squared plus 4 minus 2 squared. I believe it's square root of 8. And by the way, we'll use this distance function so much that I think from now on we'll just call it d. So just know d is this distance. But there's a reason I write 2 to distinguish it from other d's. And of course, this can be generalized to higher dimensions. So note, in general, what we can have, we just have the distance between x1 up to xk and y1 up to yk. It's again just the square root of the sum of squares. Square root, if you want, of y1 minus x1 squared plus yk minus xk squared. And with this distance, in fact, rk and d is a metric space. And in fact, we can generalize the previous thing to, Rn, or the book calls it Rk. So note, there's also Rk and d, where the distance between x1 up to xk and y1 up to yk is just the square root of the sum of squares. So y1 minus x1 squared plus yk minus xk squared. Okay, so that is one possible metric or metric space for R2, but there's other ones that are even more interesting. So consider the following one. So R2 and D1. And I'll explain in a second what this is, but D1 will sometimes be called the taxicab metric for reasons that will be apparent in a second. So let's take x1, x2, and y1, y2. Then d1, all that it will be the sum of the distances of each leg. So d1 will be this plus this. In other words, to make this more formal, d1 of x1, x2 and y1, y2 will just be the sum of the absolute values. So y1 minus x1 plus y2 minus x2. In other words, you take this distance, which is y1 minus x1, and you add it to this distance, which is y2 minus x2. Now, why is it called the taxicab metric or the Manhattan metric? Because if you want to get from this destination to this destination with a taxi in Manhattan, usually there's a building in the middle, so you can't just cross this. This is not Grand Theft Auto or anything. So what you do, you first go one block to the right and then one block up, and you go to your destination. So that's usually how your taxi fare is calculated, at least back in my days. Okay. I think things have changed. And also similarly, there is something called the infinity metric. Okay. So R2 and then D infinity, which simply is as follows. So D infinity of x1, x2, y1, y2, it's just as follows. So it also has to do with legs of triangles. So suppose this is x1, x2, and then y1, y2. Now, again, consider the legs of the triangles, and all that this infinity thing is saying, it says take the bigger leg. Okay? So in other words, it's the bigger one, or the maximum of those two distances. So what was it? Y1 minus x1 and y2 minus x2. So in other words, this is one, in this case, it's the infinity distance between the 2 points. I don't know what it's useful for, but just to show you there are other exotic metrics on R2 or on R. And last but not least, so a very strange metric, but still really cool, it's what's called the discrete metric. So take R and D, but then D is very weird. So it says either the point is the same, so 0 if x equals y, or everything is 1 apart. In other words, everything is a distance of 1 apart. And it's kind of weird. It's really the social distancing metric in some way. It's like everyone from you is just 1 away. Which is, again, not a very natural thing to consider, because technically points are usually closer than other ones, but this is really saying every point is 1 apart. And by the way, this is an excellent source of counterexamples, so definitely remember this for counterexamples. But again, even though this seems unnatural, there is a more natural way of picturing this. Take, let's say, 1, 2, 3 with the same metric. Then that space is just the equilateral triangle with vertices 1, 2, 3. Because you see here, really, it is true that every point is exactly 1 apart. So now we've seen lots of examples of metric spaces, and therefore really understand that everything that we'll show from now on will hold true for all 10 examples all at once. So we're literally killing 10 birds. No, we're killing 10 birds, and so really understand, okay, that everything we'll prove from now on will be true for those 10 examples. So in other words, we're really killing 10 birds with the same stone. Imagine that. All right, thank you very much.